So, in our last video, in 1.4, we learned what it means to take a derivative. The derivative is an instantaneous rate of change, and we can find the derivative by taking the limit as h approaches 0 of the difference quotient. Now, we can do this without a specific x value in mind, and then just have a function that represents the derivative, or we can do this with a specific x value in mind, and that would represent the derivative of the function at that specific x value. Regardless, though, this ends up being a good amount of work, especially as we get into more complicated functions. And so we don't really want to have to do this every single time whenever we have to calculate a derivative. Because as soon as I change my function a little bit, then I have to go through this process all over again. I have to find the difference quotient again. I have to take the limit as h approaches 0. So what that might lead us to is, are there any properties of derivatives or rules that we can use to make our lives a little bit easier? Well, it turns out there are. Okay, there are some very basic derivative rules that are really going to help us out. So, first off, our first important basic derivative rule is called the additive property of derivatives. Okay? And I'm going to put in parentheses subtractive, because this also applies with subtraction. Okay? And that is, if you are taking the derivative of two functions that are being added or subtracted, I'll go ahead and put this plus or minus. Okay? If you're taking the derivative of these, this is new notation. D over dx means you're taking the derivative. You're finding how this is changing as x changes in an infinitely small way. Okay, so this represents taking a derivative. Okay, so if I take the derivative of two functions that are being added or subtracted together, it turns out all I need to do is just take the derivative of the first function, take the derivative of the second function, and just add those two things together, or subtract if you're subtracting, right? So it's as easy as just focusing on each function individually, taking the derivative of each of them, and then combining them, how they work. Okay, so that's the additive property of derivatives. So that's nice. That makes our lives a little bit easier. The second property that we're going to talk about is, I'm not sure if this one has a name, but I'll just say this. This is constant multiplication. So if you have a function, and that function is being multiplied by some constant, c, okay? And then I want to take the derivative of this. Well, it turns out, if it's just a constant being multiplied by the function, you can ignore that constant and just take the derivative of the function and then multiply by that constant on the outside. You can kind of just pretend that constant's not there and take your derivative like normal and just keep the constant where it was. Okay? So, what does this tell us? This tells us that addition and subtraction doesn't complicate your derivatives, as well as if you multiply by just a constant, that also doesn't complicate your derivative at all. Well, why is this helpful? Well, that tells me, let's go back to the function we looked at yesterday. Let's say I'm working with f of x equals 4x minus 3x squared. Well, I've got a polynomial here, but according to my properties that I just looked at, if I wanted to take the derivative of this, what I can do is I can, according to my subtraction property, my subtractive property, is that subtraction isn't going to complicate my derivative. That means I can just focus on this function, take the derivative of that function, and then focus on this function, take the derivative of that function, and then subtract the two together. And both of these functions are more simple than everything together. Okay. Well, now in that case, let's just zoom in on, this one. So if all I have to do, based on that subtractive property, to find this derivative as a whole, I can focus in on this derivative. Well, what's the derivative of 3x squared? Well, according to my constant multiplication property, we'll go and put a little property at the end of that. According to that property, this 3 that's in front doesn't complicate the derivative. That means I can ignore that 3 and just, I always forget to go back, and just focus on what's the derivative of x squared. So these two properties, the additive property and the constant multiplication property, means that if I have a big, long, complicated function, I can narrow things down to where I can focus on smaller functions and just ask, what's the derivative of those smaller functions? Okay? So these properties become very handy in tackling complicated functions. Okay? So let's look at what's my derivative of x squared. Okay? Let's try this out. Let's actually go through my process of the difference quotient to figure this out. Okay? So my function here is going to be x squared. Let's see if we can find the derivative. Okay, well that's going to be x plus h squared, okay, because that's your f of x plus h, minus just x squared, because that's your f of x, over h. Okay, well, let's go ahead and multiply things out. X plus h squared is x squared plus 2xh plus h squared minus x squared. Sure enough, like what usually happens with difference quotients, the terms that don't have an h in it, subtract equals 0. And I'm left with 2xh plus h squared over h. Now, every term in the numerator has an h in it, which means I can factor out an h. And the h's cancel, and I'm left with, I'm left with the limit as h approaches 0 of 2x plus h. Since I've gotten rid of my discontinuity, I can go ahead and plug 0 in, right? I can go ahead and let h approach 0, and I'm left with 2x. Right? 2x plus 0 is just 2x. So there's my derivative. So it turns out, if my function is x squared, then my derivative is 2x. Well, let's try this again. Okay? Let's try this again for x cubed. What about if fx is equal to x cubed? Okay. What happens? Well, this one, the computation takes a little bit more time, but it's still relatively straightforward. But I will go ahead and skip to the end. It turns out, if you kind of follow this through, you get f prime of x is equal to 3x squared. So I could keep going with like x to the 4th, x to the 5th, but what I can see is that there ends up being a pattern. With a lot of these derivatives, and if I'm looking at a specific like family of functions, I can actually see patterns. So what this leads us to is I have a rule for this specific family of functions called power functions. So this is called the power rule. If my function is in this form, x to the p, where p is some power, so this could be x squared, x cubed, x to the fourth, x to the fifth, then the derivative ends up always following, it always follows the same pattern. Turns out that the derivative ends up equaling, you bring the p in front as a constant, whatever the power is, you multiply it by that power, and then you decrease the actual exponent by 1. So we can see that here, right? I brought the 3 down, I'm multiplying by 3 now, and then I subtracted 1 from the exponent, and I got 2. This one's a little less obvious, but the same thing's happening. I'm bringing the 2 down in front, and then I'm subtracting 1 from the exponent. X to the first, though, is just x, so I don't actually need to write the exponent anymore. Okay. So it turns out this power rule also works with linear functions. Okay? If your function is just x, what would your derivative be? Well, x is the same thing as x to the first. So if I use my power rule, I'm going to bring the 1 in front, and I get 1 x to the, and then I'll subtract 1 from the exponent, and I get x to the 0. Well, what's x to the 0? X to the 0, anything to the 0 power is equal to 1. So this is just 1, because 1 times 1 is 1. So it turns out that if you have just x, then the derivative of x is 1. Okay? Very nice. Okay. So why is this power rule helpful? Well, because we now have this power rule, if I combine that power rule with my additive property and my constant multiplication property, this allows me to tackle any sort of polynomial. So, for example, let's look at this. 2x to the fourth minus 3x cubed plus 5x minus 19. What's the derivative of this? Well, according to my additive property, right? So this, I really don't, I guess, let's back up. I really don't want to use a difference quotient for this. That would take me so much time and so much computation. I don't want to have to use a difference quotient. But that's what's nice about my properties and my power rule, is that I can use those to almost take a shortcut in calculating my derivative. Okay? So, according to my additive property, or additive subtractive property, if I want to take the derivative of this function, right? If I want to know what the derivative is, I can focus on each, I can focus on each of these pieces individually. Anything that's separated by addition or subtraction, you can focus in on those pieces individually. Okay? So, if I look at this piece, what's the derivative to x to the fourth? Well, once again, the constant out in front, I can just leave there for now. And then I can just focus on just x to the fourth. What's the derivative of x to the fourth? Okay, I can leave the 2 there because of, once again, that's because of my constant multiplication property, right? So now I can just focus on an x to the fourth. Well, that's a power function. I can use my power rule. Okay, so what does that give me? That gives me 4x to the third. I multiply by what the exponent was, and then I subtract 1 from that exponent to get my new exponent. Okay, moving on. Now let's focus on this term. Like, similarly, I can just keep the 3 there and then focus on what's the derivative of x cubed. Well, I'm going to bring the 3 out in front and then subtract 1 from the exponent. I get 3x squared, right? That's one we already went through. Next, I'll focus on this piece. What's the derivative of 5x? Once again, I can just leave the 5 there and focus on what's the derivative of x. Well, we just saw that. The derivative of x is just 1. Last but not least, I have this 19, this constant. What do you think the derivative of a constant is? Well, this is another property that's always true. If you just have a constant and you're taking the derivative of a constant, turns out your derivative is 0. Why is that? Because if you have a constant function, what's my rate of change? It's not changing, right? The function is staying the same. If it's not changing, then your rate of change is 0. Your y value is not going up or down as your x moves along. So, the derivative of any constant function is 0. We'll go ahead and put that over here. Okay, if f of x equals a constant, then f prime of x is equal to 0. Then the derivative is equal to 0. Perfect. So now I can clean this up a little bit. 2 times 4 is 8. 3 times 3 is 9. 5 times 1 is 5. And I don't need to write the minus 0. And there's my derivative. That was so much less time than trying to do a difference quotient for this long, complicated polynomial. So from now on, honestly, we really don't have to do that difference quotient anymore. We still learned it because that's where derivatives come from. But from here on out, we can use these nice shortcuts to find derivatives much quicker than using a difference quotient. Okay, so you can go ahead and pause the video, try out a few of the homework problems that deal with just these nice simple polynomials before I've got a few more examples to talk about. So, this power rule doesn't just affect polynomials, though. Take a look at this function. What about the cube root of x? What's the derivative of this function? Well, anytime you see a root, you can actually write roots as power functions. I can rewrite this as x to the 1/3. Okay, so a cube root, so a square root is x to the 1/2. A cube root is x to the 1/3. A fourth root is x to the 1/4, and so on and so forth. Right? So that's how roots work. You can write them as exponents, which means that this is a power function. And that means I have a nice rule for calculating the derivative. So, my derivative, I'm going to bring the exponent down, 1/3 x, and then I'm going to subtract 1 from the exponent. What's 1/3 minus 1? Careful, it's not 0/3, because that would be subtracting 1/3. 1/3 minus 1 is going to be negative 2/3. Are we okay with that? 1/3 minus 1. Well, 1 I can rewrite as 3/3. And that gives me the negative 2/3. And so there's my derivative. So anytime you see a root, you can think of that as a power function. This is also true if you ever have a power in the denominator. What if you have something like this, 1 over x to the 4th? If you ever have a power function in the denominator, this still qualifies as a power function because you can rewrite this using negative exponents. If you remember, this is what negative exponents represent. Negative exponents represent that you just have the power function in the denominator. You're dividing by that power function. Okay, so since I can rewrite it in this power function form, so this is also a power function, which means my power rule applies to this as well. F prime of x, I'll bring the negative 4 out in front, and then I will subtract 1 from the exponent. Negative 4 minus 1, careful, is negative 5. I've got more negative. So it works. Very nice. So this power rule works for roots and works for functions where you have a power function in the denominator. Okay? So let's put it all together. What if you have f of x equals 1 over the cube root of x to the 5th? Ugh. Doesn't look very pretty, but as long as I can write it as a power function, I'll be fine. Okay? So how do I write this as a power function? X to the, well, it's in the denominator, so I know it's going to be negative. Since I'm taking the cube root, I know I'm going to have a fraction, and the denominator of that fraction is whatever the root is. The numerator of the fraction is whatever the power of the x is. Okay? Notice our numerator up here was just 1, and that's because x, since x didn't have a power, we can always just put a power of 1 there, right? I can always just think of that as x to the 1st, and that's where this 1 comes from. Perfect. So once again, as long as I can write it in that power function form, then the derivative is fairly straightforward. Negative 5/3 x, and then I subtract 1 from this, which is 3/3, and I get negative 8/3. Okay. Okie doke. Go ahead and try that homework out, and let me know how you do. Thanks, guys.